Well, hello again. Today I'm going to use an analogy to try to explain some more details about how caching works in our system. And then hopefully after going through this analogy, we'll be able to think about all the technical details involved in cache use in our system. So I'm going to follow on some of the things that were in the last presentation by using this analogy and then introducing a few more pieces of nomenclature using this analogy as well. So here we go. So now suppose that in a non-COVID world, you were doing some research and you have a very small apartment in which you're going to be doing your work. And you live a couple blocks from the library. You've rented out this apartment from a library nearby, and you really want to research a collection of books in this library. And it's a fairly big collection, and you can't really check out the entire collection at once in your small little apartment here. So you're going to try to do your best at getting some of these books at a time in order to conduct your research. So let's say that here's the collection of books in the library that you hope to do most of your work from. And so this collection of books we could think of as being analogous here to the main memory of our program. And suppose you start out by saying, okay, I've got a small shelf that'll hold 4 of these books. So this is going to be analogous to what we call a cache set. So I can check out and bring home 4 books at a time. So I can get one set of books. And so in this analogy, a set of 4 books is analogous to a block of memory with a certain number of bytes, like those blocks that we went over in the last presentation. So we could use something called direct mapping in order to figure out how I might access 4 books at a time. And so we want to think about what kind of mapping can we use between this single cache set and our entire set of books. And the way to do this is to say that, well, I've got one cache set of 4 books called set 0. So I'm basically going to give tags to 4 books each and mark them as set 0 with a particular tag. This now makes every 4 books in the entire memory collection, if you will, is able to be uniquely identified by a set and a tag number. And so we can now know which set of 4 books is on my shelf at any time by knowing what set and tag number it comes from. So this is the basic idea. And then when accessing an individual book in the set, I also can think about book 0, book 1, book 2, and book 3 in any set of 4 books. So this is now a fixed mapping between the books in the library and my set of any 4 of those books that I can hold at any time on my shelf. So this is what we call simple one-way direct mapping. In this case, I had just one set, set 0. But I could open up more shelf space in my apartment. And this would be analogous to increasing the number of sets of cache. So I could do something like this, where I say, well, let's have 2 shelves in my apartment. And one would be designated set 0 for a subset of books, and one would be designated set 1. This would enable me to essentially go and check out 4 books, but then go get 4 more without returning the first 4 that I checked out. And so what kind of mapping could we do then? I've got 2 shelves in my apartment. Each one is designated set 0 and set 1. So now I've basically got 2 cache sets. So I've sort of doubled my amount of cache, if you will. And when I do that, really the mapping now changes. And so it looks like this. So I've got a space for set 0, tag 0, the first 4 books that I could put on my set 0 shelf. And then I've got space for set 1, tag 0. And so you see here what's happened is we've doubled the cache, so we've halved the maximum tag number because we have twice as much availability of books to stay in our cache as we had before. And so we just simply have a whole series of tags for set 1 shelf and a series of tags for the set 0 shelf, you see here. Okay, so now this is a new fixed mapping because I changed how much cache I had. So that's an interesting thing to note about this. So now if we stick with this mapping for a bit here, let's see what happens if I go ahead and decide, okay, I'm going to start doing my research. I'm going to read the books, and I'm going to start with the first 4 books here. So I'm going to go to the library, and I'm going to get out these first 4 books, and I'm going to put them on my set 0 shelf. And so that's how it would go, and I would be able to then read these 4 books without going back to the library again. So if I started on the 0th book here, I still can read the first, second, and third book without going back to the library. And now, so I've got those first 4 books. Now, if I want to start reading the next 4, because I've finished these first 4, I've gotten through this one, and I really want to go ahead and start looking at the next one. Well, what am I going to be able to do? Well, what I'm going to be able to do is go get the next 4 books from the library and put them on my set 1 shelf. I don't have to return the previous 4 books now that I have this second cache set available to me. And that might be good because maybe when I'm down here reading, I need to refer back to one of these previous books, and I would still have it. And so that would be useful. And even within this set of books, if I'm over here, I'll still be able to refer back to one of these. So that would be very, very good. And that's how a cache can help me out even when doing this research. So, and can you see the pattern here? Where will the next 4 books from the library be placed? So if I want to go ahead when I'm finished with this one and I really want to start reading this one over here, what's going to happen? Well, it's going to have to get placed on the upper shelf, and this set of books from tag 0 is going to have to get evicted in order for me to place the set 0 tag 1 books on this shelf. So I'd have to return these and then go check out these. So, so that's how that would work. Now, now that we have this mapping, let's consider something else that we could do here. we could find some more shelf space in our apartment so that we had extra space. And what we would want to do here, we have our 4 shelves, each which would hold the 4 books. But instead of saying that we're going to increase the number of cache sets, what we're going to do instead is sort of hold on to these as extra places. So in that last case, when I was getting set 0 tag 1, maybe I'd want to hold on to set 0 tag 0. So in order to do that, I could do that by making these as sort of backup areas. And so I could still have this upper 2 shelves as our set 0, but with a backup plan. I could hold on to more books from the overall sets. And same thing down here, I could have a set 1 shelf with its backup shelf. Now this is analogous to what we call a two-way associative cache. So we've got 2 places to put a particular tag of books from each of these sets. So these in cache terminology are called lines. So this is 2 lines now, and that's why it's called a two-way associative cache. And it's associative because we still are associating these lines with particular sets and tags. And so the overall number of sets is the same. And therefore, this mapping also stays the same. So we do not change that. So we've got a fixed mapping that hasn't changed. We've just opened up some extra space called lines as backups. Okay, so now that we have this sort of arrangement, let's start thinking about how this might get used in terms of accessing these. Hopefully you can see that with the extra lines, we are able to hold more books from our main memory depending on how we access them. It might work out for us, it may not, depending on our access patterns, and we'll see a little bit more of this later on. But now, how do we actually refer to any book in this collection that we happen to want to access and read? Any particular book has to be designated by its set, its tag, and its book number. So this book right here is designated as set 0, tag 0, book 3, because these books are 0, 1, 2, and 3 in this set. And so we can think of an address for any book as being associated with its set, its tag, and its book number. And this is analogous to what we're going to call a cache address for any byte in our memory. So now we might keep the same type of cache, but our memory might get bigger. And so maybe we're going to actually want to look at more books in the collection. We've expanded our research, if you will. And when we do that, the mapping changes. We still have the same set 0 and set 1 you see here, but now we go through and we get down to the original tags we had, and then we start with new tag numbers for the rest of the memory that we're going to access. So suppose we have this given situation, and now I'm going to try to read books from this collection. But in this case, what I'm going to do is I'm going to read them in a random way. So maybe I'm going to start right here. So my first book that I want to look at is in set 1, tag 2. And so I'm going to go to the library and I'm going to go get that whole set and put it on my set 1 shelf. And this particular book is book 012 of this set. And so if I'm going to go start reading that book, this book right here, once it's been put on my shelf, in order to know to put it on that shelf, the address of that particular book would have looked like this. Tag 210. So I'm putting these in binary. The set is set 1, so that's a 1 there. And the book number is book 2, that's 01 here. Now, in our nomenclature for actual cache, you'll see in your book that each of these pieces of the address come in this order, T, S, and then B, and they're referred to, each of these pieces in your book, as CT, CI, and C0. So just so you know, going forward, that's what these are for, is to indicate the pieces of this overall address. So now, suppose we want to start looking at another book in a fairly random way. So we're going to go down here to set 1, tag 4. Well, one of the nice things about having this extra line is that I now can bring in set 1, tag 4 in without having removed the previous set. And so now the address there, here's tag 4, 100, still set 1. And now this is book 3, so it's 11. And because it's this third book right here. Okay. So now let's say that my next random access of these books is this one up here. So still in set 1, but now tag 0 and book 1. Now we have a problem here, because if I go to the library and I keep up my my way of doing things here, I'm really going to have to return one of these. And so what I could do is return this one and then get out the other set and bring it home, and that would be set 1, tag 0. Now you can kind of see some of the issues with this permanent mapping. The permanent mapping makes this system really fast, but it does have some problems when you access things in a more random fashion like this. We essentially, for the first two, had what are called our cold misses, right? But for this third one now, it's a pure miss. We had to decide which one of these two shelves we were going to use. And overall, for random accesses then, we can tend to have a fair number of misses. Even though we might have been tempted to be able to use these shelves, we simply cannot, because we have this fixed mapping, and this is how our system works. Now, that address, of course, is going to be now our tag 0, set 1, and then book 1 of this set. So what you see here is that this random access of these pieces of memory resulted in misses to our cache. First, in terms of just cold or compulsory misses to bring something in. And then finally, a plain old cache miss because we had to replace something. And we had to choose how to replace it. And the interesting thing here is that we chose what's called the least recently used replacement policy. So this set with this tag was replaced now because it was the furthest away one that we had previously accessed. And that is the most common way that our caches work. We chose to remove the one that we accessed the longest time ago, and that's called the least recently used policy. So now with this analogy, I've introduced some more nomenclature, plus talked about some of the nomenclature from the previous presentation. Now we're poised to get into the real thing, the exactly how cache on our system works. But hopefully you have a sense for some of this nomenclature now of how we set up our cache and how we have this mapping that gets done based on how many sets we have total in our cache on our machine. And so we will next do a more detailed look at exactly how it works on our system.